We'll continue with our online lecture series. This is Power Electronics lecture number 40A, and the topic of today is SCR commutation circuits. So basically, we will be studying circuits which can turn off SCR forcefully. Okay, so we have discussed circuits which can turn off SCR naturally. In rectifiers, the SCR turn off naturally because of the negative half cycle. Fine. So how do you define commutation? Commutation is defined as the process of turning off an SCR. All right, let's revise what is the characteristics of SCR in the first quadrant. So we have region number one, which is the forward conduction state, and region number two, which is the forward blocking state. All right. So what do you mean by turn off? Turn off means you have to forcefully make SCR to leave from the conduction state and enter a forward blocking state. Meaning you have to go from one to two. Are you understanding? You're turning off something, not turning on. So SCR being on being it's in the forward conduction state, and SCR being off means it's in the forward blocking state. So we have to bring it from forward conduction to forward blocking mode. Okay, so that's what I've written over here. Turning off an SCR means bringing the device from forward conduction state to the forward blocking state. Okay, so there are two techniques. This is very, very crucial for oral exams also. SCR turnoff requires that its anode current falls below the holding current. That's one way to turn off the SCR. The second way to turn off the SCR is whenever a reverse voltage is applied across the SCR for a sufficient time. Okay, so that means we can say SCR is reverse bias. So what do you mean by reverse bias? Negative voltage is applied to the anode and positive voltage is applied to the cathode. That means this SCR is reverse bias. When this happens, then also the SCR turn off. So what are the two techniques? Anode current fall below the holding current, and second technique is the reverse voltage is appearing across the SCR anode and cathode terminals. Is this point clear to you? Immediately let me know. You have understood what do you mean by commutation and how to turn off an SCR and what are the two techniques. Can I proceed?
Yes, sir.
Okay, fine. Now this is also very, very important. What are the two commutation types? So first is natural commutation, right? And then we have forced commutation. So in natural commutation, it will make use of alternating reversing nature of AC voltages. As you can know, in case of AC voltages, you have positive cycle like this. Oh, sorry. You have positive cycle and then you have negative cycle. All right. So whenever we have a negative cycle, this means that the current passes through a natural zero. So also and simultaneously a reverse voltage appears across the SCR, making it reverse bias, and then hence turning off immediately the device. So in case of natural commutation, no external circuit is required. So it is the simplest and the most widely used. So it is the most often used technique in case of rectifier, control rectifier. So all the control rectifiers use this natural commutation of SCR to turn it off. Okay, I hope you have understood this. Then in case of forced commutation, now where this is used, wherever the input supply is DC. Okay, so wherever you have a DC input source, because for a DC, we don't have a negative, it's always positive, right? And so the two techniques will be to reduce the anode voltage below the holding current, or a reverse voltage should appear across the anode and the cathode terminals. Okay, so in case of forced commutation, you're forcing the SCR to turn off, and most often the commutation components are LNC. Okay, and when you compare between the two, this force commutation makes use of external circuit to make this anode current uh, forcing towards zero, or we can make the anode current less than holding current. All right, so this external circuit required for turning off an SCR is known as forced commutation, and I've written very clearly over here. that it is used in case of whenever the input is DC excitation. That means at the input we have a DC input. Okay. So again I revise: natural commutation and forced commutation. Forced commutation, you require external circuitry which consisting of commutation components such as capacitor and inductor. In fact, I will go one step further and tell you now that you require a auxiliary SCR to turn off the main SCR also. So that also can be a commutating element. All right. So commutating components along with LNC, and you make external circuitry so turning it off. So this distinguish is also very, very important. You should know what do you mean by natural commutation, and you should know what do you mean by forced commutation. Okay. So any doubt on this before I proceed? Yeah. Any doubt in both the techniques? Please let me know.
I did not understand the second point.
What did you not understand?
That no external circuit and external circuit means natural circuit, the thing is happening within the original circuit, and in force I think an extra circuit or device is required, right?
Yeah, because SCR is not turning off on its own. In case of AC, the input is going negative. So negative voltage might appear across the SCR to turn it off. But in case of DC, your supply voltage is normally positive. So how will you turn off the SCR? So to forcefully turn off the SCR, we will require to use a external circuitry. So we will be discussing that force commutation techniques now. I've asked you the question whether you have understood the difference between them. This force commutation techniques I'll be teaching you now. That is class A, class B, class C, class D, and class E. Class F is natural commutation. Is this distinguish clear to you? Yes?
So
Okay. Now let me proceed to the next one. You may note this down in your books. So that's what I was talking about. SCR commutation circuits. So basically, there are around six techniques, or actually five techniques to turn off an SCR when input is a DC. When input is a AC, we have line commutation, which we have already discussed in the control rectifiers. So SCR connected when the input is AC are all using line commutation for SCR turning off. But when the input is DC, you have to forcefully turn off the SCR, and in that we are calling it class A commutation, which is called as load commutation. Class B commutation, which is called as a self commutation by LC circuit. Class C is called as complementary commutation. Class D is called as impulse commutation or voltage commutation. Class E is called as external pulse commutation. Okay, and class F is line commutation when the input excitation is AC. All right, so please note it down. So this is an important topic. Either they can ask you a theory question, or they can even ask you numericals, because we have formulas also for these commutation techniques. So yeah, it's another important topic, and there is always a question from commutation circuits in the exam, either for 5 marks or 10 marks, or max to max 15 marks. So this topic is really important. Okay, have you noted down?
noting it down.
Okay. Now, in case of class A commutation, it's also called as resonant commutation. It's also called as resonant commutation, or it's also called as load commutation. Can I proceed?
Second.
Okay. So now please, concentrate on the circuit now. So very simple circuit. Can we begin? So you have to give me 5-10 minutes to explain you this, and then you can note down whatever you want to note down. Anyways, this PDF will be available after the online lecture. Okay. So now, see, turning on the SCR. What are the turn on techniques of SCR? Anyone can tell me how to turn on an SCR? Some of you have written the answers in the exam also. How to turn on an SCR? It has to be in the forward blocking mode. That is the condition. Yeah, yeah, that is the condition. What are the turning on techniques? Correct. Then next, see, for ISC exam, I have taught you two techniques, that is gate triggering and dV by dt triggering. All right. But there are other techniques also. There is light triggering also. So some SCRs also triggered by light. So that is also one of the techniques to turn on an SCR. Okay. So anyways, so we are
There are
sticking to
three
the gate.
methods. Three methods: gate triggering, forward voltage, and dV by dt triggering.
This I have taught you for ISC exam. But other than this, you have light triggering also. That's what I'm informing you right now. Okay. So these are called as light activated SCRs. So that is out of the scope, but one technique is there. One more technique. But here we are following gate triggering. That means we apply the gate pulse to trigger on the device, to turn on the device. All right. So over here, what do we have? We have a DC source V1. We have SCR named as T1, and we have a RLC in series. Okay. LNC are the commutating components. Okay. The commutating components are LNC. Means this will help to turn off the SCR. R is the load and T1 is the SCR. All right. Now, whenever you remember RLC, what comes to your mind? RLC series circuit, right? So, what is the speciality of RLC series circuit? Anyone can tell me? What is the speciality of RLC series circuit?
That it can be used in both continuous and discontinuous mode.
No, that is there, but RLC series resonance you must have heard, right? It produce, underdam, overdam, on critically dammed oscillations. That's what it is famous for. All right. So this circuit will also do the same. So let us begin to understand very, very slowly. All right. So whenever the SCR turns on, let's say at time t equal to 0, SCR T1 is triggered immediately. Okay, by the help of a gate pulse. So gate trigger circuit is not shown over here for simplicity. Now, as SCR1 turns on, the circuit looks like this, as shown in figure 1.2. So we are assuming that SCR is a ideal SCR, and when it is on, the ideal voltage across it is 0. Practically, it's around 1 to 2 volts, but we are assuming it for simplicity that SCR behaves as a short circuit when it is turned on. So what do you see over here is you see a DC source and a RLC series network. All right. So the load resistance is R, and the commutating components are so selected that they form a underdamped resonance circuit. Now, what do you mean by underdamped resonance circuit? I'll cut the long story short. Underdamped resonance means the oscillations which are produced are reducing in amplitude continuously. Okay. So eventually, after some period of time, it will be reducing towards 0. So that is what you mean by underdamped resonance circuit. All right. When such a circuit is energized by a DC source V1, a current of the nature as shown in the figure 1.3 is obtained. Okay. Now, what is the speciality of this current? I mean, this current is the anode current flowing in series, right? And yeah, this current is going below 0. That means at time t equal to 1, at time t equal to t equal to t1, your anode current is becoming 0. Will this turn off the SCR? Anode current becoming 0. Will this turn off the SCR? Yes or no?
Yes, sir.
Yes, because one way to turn off the SCR is make the anode current below holding current. Now holding current is around, let's say, 10 to 15 milliamperes. So here is going 0. So definitely we are forcing the SCR to turn off, right? Because this RLC circuit is forming an underdamped resonance circuit, and the oscillations are like this. So as soon as the current reaches 0, the SCR will turn off, okay, immediately. So yeah, as the current IA decays to 0 and tends to reverse. So after this it tends to reverse. Before that only, as soon as the anode current reaches 0, the SCR T1 will turn off on its own. Okay, because we have connected this RLC network and we have connected in such a manner, their values are selected in such a manner that they form a underdamped resonance circuit. Okay, so this is how your SCR is turned off forcefully in class A commutation. Any doubts? So T is called as the period of the underdamped oscillations. So T1 is around T by 2. At T equal to T1, your IA is 0. IA is actually anode current flowing through the SCR. What is T given by? Anyone can tell me what is the frequency of oscillation for a RLC series resonance circuit? Do you remember from your theory? Omega equal to square root of L into C. Do you remember this formula?
Yes, sir.
Yeah. So omega is square root of L into C. So what will be F frequency? Frequency is 1 upon, I mean 2 pi F, right? Frequency omega is 2 pi F. So frequency will be square root of LC divided by what? 2 into pi into F is equal to square root of L into C. So what will be F? F will be square root of LC divided by 2 pi. Now we can write it as T. Now what is T written by? T is 1 upon F, right? Yes or no? So T we can write it as 2 pi into square root of LC. So the time period of the resonant RLC circuit is 2 pi square root of LC. And T1 is half of T by, I mean, T1 is T by 2. So if T is 2 pi square root of LC, T1 will be pi root LC. Is this point clear to you? Yes, no? Quickly tell me so that I will move on to the next topic.
Yes, sir.
Okay, good. Yeah. So beyond time t equal to t naught, the current I is reversing in nature. This is, I think we are calling this as t naught. Actually, this should be t1. It's by mistake I've written as t naught. Let me check. Yeah, I guess that value is t1 only. So beyond time t equal to t1, this is 1. So what is happening as you see in the waveform, beyond T1 the current is going negative. So already the SCR is turning off at T equal to T1 because at T equal to T1 the current is becoming 0. So SCR is definitely turning off, right? So SCR when on, now this is something more. So this is what is all about when they ask you what is class A commutation, draw the circuit diagram and explain. That's what you have to explain. That's it. Now whatever we are discussing is the analysis. All right. So class A is possible in DC circuits and not in AC circuits. That is a very, very important point to remember. Another point is SCR T1 when on carries the charging current of the capacitor, which will soon decay to a value less than a holding current, which will switch off the SCR. So exactly that is what is happening. That is how the series resonance circuit works, right? Because here what happens is LNC works in tandem. So if one is storing energy, others releasing the energy, and the vice versa. All right. So that's the working of RLC series resonance circuit. The time for switching of the SCR is determined by the resonant frequency. And what is the resonant frequency? 1 upon 2 pi square root of LC. Okay. So which in turn depends upon LNC. Do you remember few lectures in the last online lecture we have discussed series inverter? Series inverter also you have class A commutation circuit. You remember? In series inverter we have discussed LNC component helping to turn off the SCR. In inverter also input is DC. So we are definitely going have used the commutation circuits of SCR to forcefully turn it off. Okay. So series inverter employ class A commutation circuit. Is this point clear? So if they ask you, either a short note on class A commutation or classification of SCR commutation, or they ask you to explain load commutation or resonant commutation, you have to explain these two pages. That's it. Then, uh, till here, any doubt? Any doubt in this? Okay. So we'll move on to the design consideration. This is for the, y'all don't have in detail, you have directly the formula, but still, it's nonetheless required to understand how you got the formula. All right. So whatever I've written in this color, I think purple color, it's not there for you all in the syllabus directly. You have to directly use the formula. So let me quickly revise. Whenever SCR is on, there is a voltage across the inductor, voltage across the capacitor, voltage across the resistor, and the current is called as the anode current. So let us consider this circuit. Let T1 be on at t equal to 0, and let's consider that the capacitor is not holding any initial charge, and let us call IA as I, just I, current flowing through the circuit. Okay. So what does the KVL gives you? KVL gives you that this source voltage is equal to these three voltages combined. So V1 is equal to VL plus VC plus VR. That's what we have written. Now V1 we write it as it is. What is VL? VL is L di by dt, correct? Is the inductor voltage. What is VC? VC is 1 upon C integral I dt. Current flowing, this is a series network, so current remains same through inductor, capacitor and resistor. So the VC will be given, the voltage across the capacitor will be given by 1 upon C integral I dt plus IR. Okay. And remember, V1 is the DC value. V1 is a DC value, remember that. Okay. So when we differentiate both the sides with respect to time, left hand side will become 0 because V1 is DC value. Then we get L is a constant, di square by dt square. Actually, here also should be, um, yeah, it's fine. We consider di square by dt. So plus this integral sign will go because we are differentiating. So I upon C plus R di by dt. Okay. Now we divide the entire expression by L. So we get over here di square by dt plus R upon L di by dt plus I upon LC equal to 0. Now this is a second order equation. We are just replacing di by dt as d, capital D. So we have d square plus R by L d plus 1 upon LC into I. So the roots are as follows. You remember minus b plus or minus 4ac, right? Upon 2. So that way we have to do. So d1 and d2 are the roots. So minus r upon l plus or minus square root of r upon l square plus 4 into 1 upon lc the whole raised to half. So these are the two roots. So since the circuit is underdamped, the roots are complex conjugate. So the roots are complex conjugate. Here it is. All right. So what do you mean by complex conjugate? The J term will come. So D1 and D2 will be either minus upon 2RL plus J into square root of 1 upon LC minus R square upon 2L the whole square, or it will be R upon 2L minus J into the square root, whatever you see. So this can be written as alpha plus or minus J beta. All right. So the solution to this equation number 2 which we have written, equation number 2, is as follows. I of t can be written as e raised to alpha t into a into sine beta t plus b cos beta t. All right. And due to inductor, the current flowing at I equal to 0 plus and I equal to 0 minus is 0, because inductor will not allow to change the current so easily. So I of 0 will be e raised to 0, a sine 0 plus b cos 0. So from here you will get the value of b, because I of 0 is 0, e raised to 0 is 1, sine 0 is 0. So you'll get b equal to 0. All right. So I of t is given by a is a constant into a e raised to alpha t into sine beta t. All right. Where alpha is r upon 2l and beta is square root of 1 upon lc minus r upon 2l the whole square. Correct? So this IA is my anode current, which is the current flowing through the circuit, I of t. And that's how it is defined. Okay? That's how you got this waveform, uh, underdamped waveform. All right? So at t equal to t1, SCR current IA goes to 0. That means IA is less than holding current. So SCR turns off. From equation number 3, we can simplify this further. Sine beta t is equal to sine omega t. So let's say beta is equal to omega, and that means it is equal to square root of 1 upon LC plus R square upon 4L square. So omega is equal to omega naught into 1 minus alpha square. Well, alpha square is R square upon 4L square, right? Where is omega naught? Omega naught is 1 upon square root of LC. So from here we have derived actually the formula for omega naught. So F naught is the frequency of oscillations. It is 1 upon 2 pi square root of LC, where T is 2 pi into square root of LC. We have already discussed this. Whatever I am writing in the box, those formulas are important. I repeat, whatever I am writing in the yellow color box, those formulas are important. And what is the condition for underdamped oscillations? The omega should be greater than 0. That means if you satisfy this condition, that is 1 upon LC, to be greater than R square upon 4L square, then definitely this will be a underdamped, it will be underdamped oscillator. It will be behaving like that, resonance circuit. Okay. So all this is only the formulas are required, what I have marked in yellow color boxes. Okay. So formula number 3, I mean equation number 3, then this equation T, then this condition for underdamped resonance. Now, let's consider what can be the limitations of class A commutation circuit. So you can refer this class A commutation circuit. Can someone tell me the limitations of the circuit? Can you control what is T1? Can you control what is T1?
So,
No control over the commutation interval. All right, because at t equal to t1 your vc will be greater than v1, and when SCR turns off, c cannot discharge. There's another drawback. So this is the circuit. SCR is off. Let's say SCR is off, so where will the capacitor voltage go? It doesn't have a discharge part, so that's another problem. Okay. Third problem is capacitor will hold a voltage, that but SCR remains reverse bias and we can't re-trigger SCR. That means until the capacitor voltage is discharged, we cannot re-trigger the SCR. That means it is used for one-time turn off. That's it. Its SCR is on and you are turning it off once. That's it. We cannot re-trigger the SCR. Do you understand the problem? Yes or no?
yes, sir.
Okay. So solution to above problem is connect R in series, in parallel with C. So now if T1 is off, capacitor can discharge through the resistor. Are you understanding now? Same circuit, but only thing is R is connected in parallel with C. So now even if the T1 is off, capacitor have a discharge part. That means you can re-trigger the SCR if this happens. Okay. So that is what we get, a modified class A commutation. Understood this? Can we move on now? Okay. Again, there are still limitations of this modified class A commutation circuit. We have no control over the commutation interval, and the current flows through the load even after the SCR turns off. So as you can see, whenever the SCR turning off, whatever energy the capacitor was storing, it is flowing through the load again. Okay, and this currents which we are talking about are in amperes, and ampere current flowing through a resistive load or a RL load for a long period of time, it will dissipate power in the form of heat. Okay, so this is all about class A commutations. Any doubts, any queries? Okay, all right. Now we will talk about class B commutation. I told you every circuit will involve LC element, almost every circuit will involve LC element. So this is my class B commutation, or we call it as a self commutation by LC circuit, other name. Okay, so here we have a DC voltage V1, then we have a SCR which is triggered by gate triggering by applying the gate trigger pulses. Then we have a load, and here the LNC are connected in parallel with the SCR. So this is my class B commutation. I'll just little bit pick up the speed because by 8:20, 8:30 we have to finish the topics which we have in our hand today. Okay. So in class B commutation circuit, LC resonant circuit is placed across or in parallel with SCR T1. So T1 is the main SCR, I mean only SCR in the circuit. LNC are commutating components, the inductor and the capacitor, and R is the load. So let's start understanding. As soon as V1 is applied, capacitor charges through L and C. Okay, your capacitor charges through L and R, and it can charge up to the voltage V1. Okay, it can charge up to the voltage V1. So here actually I have written this wrong. SCR should be on or off? It should be off. Okay, here it should be off. So here SCR is off. All right. So when SCR is off, it's not triggered on. It's in the forward blocking mode. Why it is in the forward blocking mode? Because positive voltage is applied to the anode terminal and negative is applied to the cathode terminal. So T1 SCR is off. So when it is off, capacitor starts charging towards V1 via L and R. Now let's say SCR is triggered on. So let's say we applied the gate pulse and SCR is triggered on. When SCR is triggered on, now there are two currents in the circuit. One is current I2 via which the capacitor will discharge, and other current flows through the load, which is R, which is called as I3 over here. Okay, so the current directions are shown over here. So I3 flows through V1 positive, T1, R, and negative terminal of V1. I2 flows through T1 transistor, I mean T1 SCR, inductor L, capacitor, and back to T1. Okay. Now, the moment T1 is on, that is SCR1 is on, the capacitor starts discharging through T1 and L. Okay. So as the capacitor discharges, L charges. Capacitor stores energy in the form of electrical energy, and inductor stores energy in the form of magnetic field. So as the capacitor is discharged to zero, the current through the L has reached the maximum value. So we have a normal LC tank circuit operation, right? So now the capacitor cannot discharge further. So also L will oppose the change in the current by self-induced EMF will polarity as shown over here, right? So that means your inductor will allow the current I2 to flow in the same direction. So that means that your capacitor now, will charge with the opposite polarity. So when the inductor currents, becomes in the same direction, your capacitor will get charged to V2, V1, sorry, with the polarity as shown. So I2 is the commutating current, and I3 is the anode current of the SCR or load current, we can call it. Okay. Here there is something missing. It's inductor current becomes, yeah, here we have I2. Yeah, I'll update this, no worries. So now we have a capacitor. Across the capacitor, the polarity is reversed, right? The capacitor voltage is polarity is reverse. So due to reverse voltage across the capacitor, your C was discharging through L and T1. So I2 current is actually opposing I3 current. All right. And IH is called as the holding current. So whenever the anode current, that is I3 current, is falling below holding current, SCR will turn off, which will interrupt the load current. Okay. So whenever I3 current, see both the currents are opposing now. All right. So whenever the anode current, which is the I3 current, becomes less than the holding current of the SCR will turn off. So when the SCR turns off, capacitor starts charging to its original polarity. Okay. So as shown in 2.2. So here it is. Capacitor will again start charging because SCR is turned off. And whenever SCR is fully charged again, SCR can be re-triggered to turn on. Okay. So in summary, SCR T1 after getting on for some time automatically gets turned off. And after remaining in off state for some time, it can be again be triggered on. Okay. So this process of switching on and off is called as a continuous process. So this type of class B commutation is used in the DC chopper circuit. All right. And the drawbacks of circuit are again no control over the commutation interval, and it requires an SCR having a high current rating. Why? Because continuously the current is flowing to the SCR, the load current as well as the charging current of the capacitor. The advantage are the commutation component does not carry the load current. Okay, as you can see clearly over here, this is load current. All right. So always the current is flowing to the load. But at one point of time, this current which is flowing through LNC is not flowing through the load. It's actually opposing the load current. All right. So yeah. So in this process, as soon as you turn on the SCR, after some time, this LC tank circuit would automatically turn it off. So that is what you mean by self commutation by LC tank circuit. So that's how it will work. Any doubt in this? Please let me know immediately. Any queries in this?
No, sir.
Okay. There is one line which I have missed out over here, point number 8, which I'll complete it, no worries. Now the design considerations are as follows. I mean, this is the, uh, you know, the diagrams which we have drawn. All right. So whenever T1 is on, capacitor T1 is on, capacitor voltage is already charged up to V1. Why it is charged up to V1? Because before the SCR was off, it was charging up to V1. And now this is on. So capacitor is holding that value. And now as soon as the T1 is on, it will start releasing the energy. That means it will start to reduce. The voltage across the capacitor will start to reduce. Now applying the KVL to the circuit, what do we have? L di by dt plus 1 upon C integral 1, I mean I dt is equal to 0. So its Laplace transform will give you this, right? We can convert this into Laplace transform. L of S, I of S minus I of 0 initial value, and 1 upon C I of S upon S plus C dV dVc 0 by S equal to 0. So here we are considering I of 0 is 0 and Vc 0 is V1 minus V1. So initial voltage across the SCR we are considering to be minus V1. All right. So here we simplify this further, and you don't have all these design considerations. Okay. You have only the formula which are marked in yellow color. So again, the omega naught over here is 1 upon square root of LC. So you should remember this. All this is fine. You all can go through it. Finally, this is the important one. I of S is V1 square root of C by L omega naught divided by S square plus omega square. and its Laplace inverse will give you I of t. So I of t will be V1 square root of C by L sine omega naught t. Okay. So here omega naught is 1 upon square root of LC, which is the resonant frequency of the circuit. So what is the capacitor voltage? Capacitor voltage will be minus V1 cos omega naught t. Inductor voltage will be V1 cos omega naught t. You can check it out from here. I value you have, you differentiate it with respect to t, you will get this value. And what is the SCR conduction time? Pi upon omega naught, which is actually pi square root of LC. What is the voltage across the SCR when it is off? So the voltage across the SCR when it is off is minus V1. Okay, so let's go to the waveforms now. Waveforms are important. So I of t, as you know, it's a LC tank circuit, so it will increase and then it will decrease towards zero. All right. So what will be the voltage across the capacitor? Let's say initial voltage across the capacitor is minus V1, and then when the current reaches peak, the voltage across the capacitor reaches zero, and when the current becomes zero almost, again the voltage across the capacitor reaches 1. So what will be VT1? VT1 is on from 0 to T naught. And after T naught, as soon as the current becomes 0, the VT2 is off. I mean, the SCR T1 is off. So when SCR T1 is off, it will carry the minus V1 voltage. All right. So this waveform is important. The nature of the current I of t and the VT1 voltage. We are just checking when does the SCR turn off. So SCR turn off at t equal to T naught. So whenever the SCR turns off, it will carry minus V1 of voltage. I mean, the voltage across the SCR will be minus V1. And what is this period of conduction? Pi square root of LC. That's the time during which the SCR remains on. And omega naught is 1 upon square root of LC. That is very clear. So you should only remember the formulas which are given inside the yellow color boxes. So conduction time is pi square root of LC. This is helpful in solving the numericals. And the voltage across the SCR is minus of V1 when it is off. When it is on, we are assuming it to be almost zero. Okay. So here are some observations. You all can go through them. All right. So I have already told you all that SCR when it is on, the voltage across the SCR is zero. And SCR when it is off, the voltage across the SCR is minus V1. Okay. So again, the minus V1 is the negative voltage, which will make sure that the SCR is subjected to a reverse voltage of my V1, which will ensure its turn off. So how does the SCR turn off over here? The SCR gets turned off because the current flowing into this loop is becoming zero. And when does the current become zero? At t equal to T naught. During that time, the SCR turns off. And when the SCR turns off, the voltage across it is around minus V1. Any doubt in this? Class A, Class B combination? Yeah, students, any queries? Hello?
No, sir.
Okay, you all have to go through them once. This is interesting. This one will be interesting. So please listen. So Class C commutator is complementary commutator. Here we have two SCRs, TM and TA. TM is called as the main SCR. TA is called as the auxiliary SCR. Okay, and we are assuming ideal SCRs. And R1 is the load and R2 is the dummy load. Okay, and we are assuming that the voltage across the capacitor, the initial voltage across the capacitor is 0. All right. So let's start understanding, now here the basic principle is that once you turn on TM transistor, to turn off TM transistor, you have to turn on TA transistor. That means to turn off the main SCR, you have to turn on the auxiliary SCR. All right. So this is the principle. So here SCR-TM is carrying the load current and is commutated by transferring its load current to SCR-TA. I will explain this, how it happens. So are all of you ready for understanding the working of this? Okay, let's start. So let's trigger T1 on. So T1 is on, right, by application of gate pulse at t equal to 0. So there are two currents flowing now. One current is I1, which is flows to this loop. Another current is flowing through the resistor R2, a capacitor, and Tm. That is a main SCR. So your main SCR current is actually the addition of two currents, I1 and IC. So Im is equal to I1 plus IC begins to flow. All right. And the TA, that is the auxiliary SCR, is off during the period. So what will be I1? I1 will be V1 upon R1 in this case, and IC will be V1 upon R2. Okay. Next, so Im current will be V1 into 1 upon R1 plus 1 upon R2. Now, the capacitor voltage will charge via V1, R2, and Tm. Okay, to voltage V1. The capacitor can charge up to voltage V1 with polarity as shown over here. The capacitor will have a negative polarity on the left hand side of the plate, and on the right hand side we have the positive polarity. Okay, so now what is happening is, let's talk about the charging current. So that means your capacitor will charge via R2, C, and Tm and back to V1. So the charging current will be given by V1 upon R2. I mean, we can easily determine, it's a simple RC circuit. We have applied a DC voltage to a RC circuit. So it's not new, that you should know the formula for the current flowing through the capacitor. It's V1 upon R2 into e raised to t upon R2C, where R2C is the time constant. Now the voltage across the capacitor will be given by V1 into 1 minus e raised to minus t upon R2C. Okay. And you can refer easily that the voltage across the SCR is similar to the voltage, the voltage across the SCR T2. T2 is basically TA only over here. So TA, the voltage across the, you know, if you see the auxiliary SCR is actually minus VC. All right, this is a short circuit. So this positive voltage and this negative voltage is coming across. This positive and this negative. So that will make sure that TA is off. All right. So VT2 is actually VC of T. Now this is how the current and the voltage waveform will be. The current waveform will be decaying. It starts with a value of V1 upon R2 and it will decay towards 0. Whereas the voltage across the capacitor will be rising to, and it will be reaching a maximum value of V1. All right, given by this equation. So after some time, these are the transients. Okay, when the transients are over, your capacitor voltage will reach V1 and your capacitor current will reach decay to 0. And you know, whenever the current decays to 0, your main SCR, that is a main current, will be given by Im, which will be given by V1 upon R1. So Im will be given by V1 upon R1 as IC is decaying to 0. So to turn off the main SCR, now auxiliary SCR is triggered on. How? Now see, whenever the SCR TA is turned on, auxiliary SCR is turned on, what happens? This is a short circuit over here. And capacitor was holding the voltage V1. So this V1 will appear as it is in parallel with the main SCR. And you can see here we have a positive voltage applied to the cathode terminal, negative voltage applied to the anode terminal. That means TM or main SCR has been reverse bias. And when the main SCR is reverse bias, it will turn off. All right. Okay. So that's how it will turn off. So at t equal to t1, VTA is 0, VTM is minus V1. Okay. And now the capacitor will charge in the opposite direction. Right. So here the capacitor will charge in the opposite direction now with this polarity, plus in the left hand side and minus in the right hand side. So V1 the capacitor voltage, current will be from, capacitor will charge from V1, R1, C, and TA. So now the main current will anode current will be IC plus I2, and what will be I2? I2 will be V1 upon R2. All right. So over here we have IC, which is twice V1 upon R1, because the capacitor voltage is changing from plus V1 to minus V1. So twice V1 upon R1. I2 will be V1 upon R2. I2 will be V1 upon R2, as you can see from here. So IA will be V1 into twice R1, twice upon R1 plus 1 upon R2. Okay, so this is the anode current which is flowing. So here in this case, the capacitor charges via V1 plus R1 C TA and back to V1 minus. So the formula will be this. We have discussed this formula before, but why we have two V1 is because capacitor voltage is changing from V1 to minus V1. So that is twice minus twice V1. All right. And here negative sign indicates that the ICT current is opposite to the original direction. As you can see, ICT current earlier was flowing from the right to left. Now it is flowing from left to right. Now to turn off the auxiliary SCR, main SCR is triggered on. All right. So whenever the main SCR is triggered on, the polarity across the capacitor is like this now, and this polarity will parallel to auxiliary SCR, which to turn it off. Okay. So what are we doing here? Why it is called as complementary commutation? To turn off the main SCR, we have to turn on auxiliary SCR, and to turn off the auxiliary SCR, we have to turn on the main SCR. Did you understand this? Very simple analysis. We don't have this detailed analysis. I already told you. You have just the, you have to just write down the formula, note down the formula which are there in the yellow color. Rest all is very, very simple. I mean, the understanding part is simpler. Analysis part, you might take some effort. So this formula is also included, and this formula is also included. You don't have detailed analysis, but the formulas are required for solving the numerical. Did you understand this? Again, I repeat. First, you turn on the main SCR. All right. Let the capacitor charge. Right. It will hold the polarity in some direction. And now, in order to turn off the main SCR, you turn on the auxiliary SCR. So as soon as you turn on the auxiliary SCR, reverse voltage will appear across the main SCR to turn it off. Now, let's consider auxiliary SCR is on and you want to turn it off. So in order to turn off the auxiliary SCR, you turn on main SCR. So when the main SCR is on, the capacitor voltage will come in parallel with auxiliary SCR, making it reverse bias, and hence the auxiliary SCR will turn off. So one is turned on to turn off the other. So that is what is called as complementary commutation. So this is very, very important for numericals. The formulas for circuit turn off time for main SCR and the auxiliary SCR. So the turn off time for main SCR is R1C into natural log of 2, and T off for auxiliary SCR is R2C into natural log of 2. Okay. Here we have the control over the commutation period, which was not observed in class A and B commutation. Disadvantage is it will require a large value of capacitor to store that much amount of charge. So that's what the explanation wise it's very simple. Analysis type, you don't have to remember everything, but only the formulas which are given in this yellow boxes. All right. Any doubt in this class C commutation is also called as complementary commutation. We'll cover one more and then we'll wind up for today. Class D commutation also will cover today. Okay. Can someone give me a positive reply? Are you all there with me?
Yes, sir. Yes, sir.
You all are following? I mean,
Yes, sir.
little bit better. I mean, you will read this on your own, then you will follow it better. But yeah, okay. So yeah, these are all the waveforms which you have to, check it out properly one by one. So main SCR turning on here with red color. So as soon as the capacitor voltage is charging up till V1, all right. Capacitor voltage is always between V1 and minus V1. So capacitor voltage is rising. Main SCR is on only from here, so voltage across the main SCR will be zero. The current flowing to the the main SCR will be like this. Initially, it will be high because of di by dt rating, right? And then across the second SCR, here I've written VT1. So VT1 is nothing but VT. Let me write over here. VT1 is nothing but VTM. Okay, and VT2 is nothing but VTA. Okay, auxiliary SCR. And this is the current flowing through um, the auxiliary SCR. So here we turn on TM, that is main SCR, right? Here we turn off the main SCR by turning on the auxiliary SCR, and over here we, in order to turn off the auxiliary SCR, we'll turn on the main SCR. So this voltage, this VT1 voltages, you can note it down from the equations earlier we have described. All right. So this is the way, when the first SCR has been triggered, capacitor voltage will be charging towards V1. It will hold that value until you get the trigger pulse for the auxiliary SCR. Now, when the auxiliary SCR turns on, the voltage changes from V1 to minus V1. That means your voltage across VT1 will be going to minus VT, um, minus 2 V1. Okay, this will reach to minus 2 V1, and then it will hold that value, minus V1 value, and then again when the main SCR is on, again the capacitor voltage will start charging towards V1, from minus V1 towards V1. All right. So this is how the current, as long as the main SCR is on, the current will keep on flowing, the orange color waveform. And over in this period, the auxiliary SCR current is zero. And now, when the main SCR is off, the current is zero, and the auxiliary current will flow. So these are the waveforms for class C computation. Okay. So you have to explain the class C computation with the help of waveforms. Is that fine? Any queries in this? Yeah. Complementary computation is very interesting and it's very easier to explain. Easy to explain that. Okay. Can we move on to the next one? We will discuss now class D computation. Class D computation is the last, then we'll solve two numericals and then we'll be done for the day. Okay, fine. Okay, this is class D commutation, or we call it as a impulse commutation circuit. Later on, we'll see its other name is voltage commutation circuit also. So this is my class D commutation. Okay, we have the main SCR, we have a DC source, and we have a RL load. So this circuit which you see, let me highlight with let's say pink color. This circuit which you see, consisting of capacitor, consisting of auxiliary SCR. In fact, from this leg to this leg, okay, from this leg to this leg, and from here to here. This entire thing is my auxiliary circuit. So main circuit is V1, TM, RL load. We are considering RL load because why RL load is preferred, because we can have a continuous current or a almost constant current if the value of L is and R is adjusted that way. So here is we have of course assumption also that load current is constant, I out current is constant. So this marked portion over here, C, TA is auxiliary SCR, L1, D1 are all helping the main SCR to turn off. So can we begin with the analysis? I'm in the working. Okay. Now listen carefully. First, we initially assume that both TA and TM are off. And we assume that the initial voltage across the capacitor is V1. Okay, what is the initial voltage across the capacitor? V1. So VC0 is V1. Your Tm is the main SCR, Ta is the auxiliary SCR. Now, at time t equal to 0, your Tm is triggered on. So your Tm is triggered on. So when Tm is triggered on, the current will flow from Tm. Diode is also turned on because it's forward bias, L, and capacitor. Okay. How is Tm triggered on? By applying the gate pulse to its gate terminal. Okay. So now what happens? Which other current is flowing? One more current is flowing, which is flowing through the V1 Tm and load RL. That is I1 current. That means your main current ITM flowing through the main SCR will be I1 plus I2. So I1 is basically I out and I2 is nothing but the collector current. Now, that means that the moment the TM, the main SCR is turned on, there will be two current flowing through TM. Okay, remember that TA is off. So two currents are I1 and I2. That is I out and IC. So here I have written the directions also is the same. So if we assume that L1 and C are ideal, it is going to have LC oscillations. Now, why I've said this, it has to be ideal. If we don't have ideal, I mean, in reality, we have non-ideal LNC, right? So that's why we get underdamped oscillations. But if it is ideal, we will have LC oscillations through the circuit. So through the I2 part. So here you see the I2 current part, right? From there, we'll get the LC oscillations because here we have T1 on. So this will be a short circuit. Then we have a diode. Again, we can consider it as a short circuit because voltage across the diode when it is on is almost zero. So we have a simple LC tank circuit, L1 CV. So the peak current of the capacitor is given by IP or ICP will be V1 square root of C upon L1. So please note down this formula. Then ICT will be given by V1 square root of C upon L1 into sine omega t. So basically ICT will be IP times sine omega t, where omega naught is square root of LC, where omega naught is square root of LC. So far so good. So what we have discussed that TA is turned on, TM is turned on, and there are two currents in the circuit. One is flowing through the diode L1 and C, other is flowing through the V1, TM, and RL load. All right. Then we'll discuss about the waveforms a little later. So when we complete the analysis. So when omega naught t is equal to pi. Now let's go to the waveforms. We have come to the waveforms. We have to go through them. So now we have applied the gate triggered for the main SCR. So I out current is going to remain, constant around I naught. What about the current flowing through the capacitor? The current flowing through the capacitor will reach the maximum value. I mean, it's a LC oscillation, right? So LC oscillation will produce, current will increase and then it will reduce, decay to zero. So the maximum height of this IC voltage will be, current will be, IP, which we have already written the expression. So its duration will be pi upon omega naught. All right. Now, what will be the main current? You remember main current is, what is the formula for the main current? ITM was given by IC plus I out. And you know I out is a constant, correct? So ITM is IC plus I naught. So I naught is your constant value, and this is your IC. So that's how you get this elevated value. So this is I naught plus IP. All right. What is the voltage across the capacitor? Voltage across the capacitor, we have assumed that initially it is charged, initially it is pre-charged to V1 value. Then slowly when the LC circuit takes over, your capacitor voltage is reducing, it goes to zero, and then it starts charging in the reverse direction. We will see all these things. We'll see all these things. And till that time, main SCR is on, so the voltage across the main SCR will be zero. Okay, and these are the timing intervals. Tm is on, that is main SCR is on, then at t equal to t0, what all things happens we will discuss now. IC will become 0 and ITM will become I naught, and VC will become, assume, minus polarity minus V1. So yeah, let's begin now. Let's concentrate further. Now, okay, when omega naught is equal to pi, when omega naught is equal to pi over here, your IC of t is 0, like this over here. When omega naught is equal to pi by 2, IC of t is IP. So between t equal to 0 and pi by omega naught, ITM is I out plus IC, whereas I out is I0 and IC is IP sine omega t. This much detail you don't have, but for the diagram, you have to understanding the diagram to draw the waveforms, you require this much details. All right. At omega naught equal to pi, IC is 0. So ITM will be I naught and Vc will be minus V1. Okay. To reaching this value of pi omega pi into square root of LC of time, C will reverse its charge. And now the voltage across the capacitor will be this. Because now C has become is holding the negative voltage. It's charging in the reverse direction. So the voltage across the capacitor will be like this, minus V1. So now as Tm is on, C will discharge through C, Tm, L, D and C capacitor. So let me show it to you. Yeah. Okay. So this will charge because we have LC tank circuit, right? So whenever capacitor discharges, L will charge. So whenever the capacitor discharges to 0, inductor current will be maximum. L will oppose the change in the current by a self-induced EMF. So L will pump the energy back to the circuit, charging the current, charging the capacitor with the opposite polarity. So what will happen now? The capacitor will now charge with the opposite polarity, all right, which is called as current I2. And the main current is still flowing to the load I1, which is I out. Okay. At t equal to t naught, here we are discussing t equal to t naught over here. Okay. The voltage across the capacitor is minus V1. That means V1 charges to the voltage across the capacitor charges to minus V1. So after the capacitor charges to minus V1, diode D1 will get reverse bias. Why diode D1 will get reverse bias? Anyone can tell me? TA is again off only, because here we have positive voltage and here we have negative voltage. Remember, TM is actually a short circuit because it's on. So this negative polarity will come over here and positive polarity will come over here, turning it off. So D1 is reverse bias. So now D1 will prevent the capacitor from discharging because it has become open circuit. So capacitor will no longer discharge now. All right. So capacitor will hold that charge. Actually, this current direction I should have shown like this. Let me just mark it over here. Earlier it used to flow like this, right? Through the capacitor and the diode in this direction. And now, since the diode is off, it will only flow. It cannot flow actually. It will prevent diode D1 will prevent the capacitor from discharging. So capacitor will hold that value of minus V1. Okay. So whenever a capacitor will hold that value of minus V1 and you turn on auxiliary SCR, you turn on auxiliary SCR. So what will happen? This entire capacitor reverse voltage will appear across the main SCR, turning it immediately off. You see this voltage across the capacitor is minus V1. So this entire minus V1 will appear across the main SCR, immediately turning it off. So same old story. You turn on auxiliary SCR to turn off the main SCR. All right. So at t equal to t1, whenever the auxiliary SCR is turned on, the circuit becomes as follows. So now the main SCR voltage will be minus V1. And let's go back to the waveform now. We have reached here. Let's say we have turned on the auxiliary SCR. Current is still constant because we have a RL load. Now the capacitor current will be also constant. It will be minus I naught. The main SCR current will be 0 because it is off, and the capacitor voltage, it will hold that value, right, for some time. And the voltage across the SCR will be reaching minus V voltage, negative voltage, and it will slowly rise. This is actually called as the circuit turn off time. This time from year to year is called as the SCR turn off time. SCR will take some time to turn off until it reaches a steady value. All right. So now again the capacitor now TA is turned on, right? Now capacitor will charge with this polarity. So the current will flow like this. The I out current, load current will flow like this. Because we have a RL load, the current flowing through the load will remain in the same direction, right? So TM is off, TA is on. So the active element over here is auxiliary SCR and the capacitor. So the current part will be V1 plus capacitor, TA, RL load, and back to V1 minus. So this iode will continue until the capacitor has charged to V1 again. Okay. At T equal to T2. So where are we? T equal to T2. At T equal to T2, this is the point at T equal to T2. Your how does TA is turning off? We are discussing that. At T equal to T2, the voltage across the SCR has reached V1. Current has become 0. IC is 0. Auxiliary SCR is turned off. Now, how auxiliary SCR is turned off? Anyone can tell me how auxiliary SCR is turned off over here?
Main HCR is turned on.
No. देखो main SCR नहीं turn on हुआ है. Because the capacitor current has become 0. So whenever the capacitor current has become 0, here the capacitor current has becoming 0. So that means what your iode is also becoming 0. I mean, iode is also reducing. So what it will do? Your current flowing through the auxiliary SCR is becoming less than holding current. So that will turn it off. IC is becoming 0, na? So IC becoming 0 means what? The holding current, the anode current of the auxiliary SCR is falling below the holding current. That's why your auxiliary SCR is turning off. And capacitor will hold on to that V1 value. So this is called as class D, or it is called as voltage commutation, or it is called as auxiliary commutation, or it is called as parallel capacitor commutation. So it has various names. And from the numerical point of view, these are the important things. The turn off time T off will be given by Tm. Turn off time for the main SCR will be CV1 upon I naught. V1 is the DC supply voltage. Okay, so these formulas are important. Turn off time for auxiliary SCR will be pi upon 2 omega naught, where omega naught is square root of LC. And the peak current flowing through the main SCR will be I naught plus IP, and the peak current flowing through the auxiliary SCR will be I naught. All right. There is one waveform which I haven't explained, which is this V out. So what is the V out value? So the V out value is equal to V1. Why it is equal to V1? Here I mentioned it somewhere, I guess. Okay, yeah, I'll explain from here. Whenever the main SCR is on, do you see this I1 current flowing through the load? Correct? The outer loop. So what will be your voltage across the load? Output, RL load. The voltage across the RL load will be V1, because that is the current, that is the voltage which is appearing across the load. So the output voltage will be V1. Okay. Here I have written V1 is actually VC plus V out. Here you see V1 is actually VC plus V out. So V out will be V1 minus VC. So, initially, yeah, here it is. So here we have V1 till the time the main SCR is on. And when the auxiliary SCR is on, what is happening? This equation is coming into picture. From this diagram, V out is V1 minus VC. So V1, V out is V1 minus VC, right? Let me write over here. V out is equal to V1 minus VC. This is only when TA is on. Okay. So now this is the instant at which TA is on. So why it is jumping to T1? So if you see carefully, the voltage across the capacitor now is minus V1. So voltage across the capacitor is minus V1. So V out will be V1 minus or minus V1. That will be 2V1. And then what is the value over here? Here the voltage across the capacitor is reaching V1 value. All right. Here it is reaching 0. Here it is reaching 0. So here it will reach V1 value. And at time t equal to t2, the voltage across the capacitor is V1. So voltage across the capacitor is V1. So V out will be 0. V1 minus V1, it will be 0. So that is what explaining the output waveform nature over here. Okay. Class D commutator is slightly, not so simple, but yeah, it can be explained. It can be explained. All right. Any doubts? So this becomes the last circuit to explain. And now we'll solve some numericals and then we'll end the lecture. All right. All these boxes formulas we'll be using. Can we start? Hello. Numericals.
Yes,
Are you
sir.
listening? Yeah. So
Yes, sir.
please listen very, very carefully now. This is which circuit? Can you identify this circuit? Class D commutation circuit of SCR. All right. Just now we have studied. So you don't solve it right now, but you listen carefully and you again, I'll share the handouts. You look at the problem and try to solve it on your own. Just now we have discussed all the equations which are there, right? For all the four commutation circuits, class A to D. So in the circuit shown below, VDC value is 200, C value is 4 microfarad, L value is 16 microhenry, R is 220 ohms. Remember here we have a R load. Okay. Calculate the peak current through T1 and D. Now T1 is considered to be main SCR, na? And D is the diode. See, the arrangement of components might be different. It's in the earlier circuit here we have connected LNC, but here it is connected over here. It means one and the same only. So how we'll solve this? Given circuit is the class D commutation of SCR, right? So for a resistive load, when T1 is on, now let's consider T1 is on. T1 is the main SCR. So when T1 is on, what happens? I out will be V out upon R, right? Simple. So it will be VDC upon R. So we'll first calculate I out. I out will be V out upon R. That will be 200 upon 10. That will be 20 amperes. Now, what will be IP? IP is nothing but the peak current flowing to the capacitor. That will be, remember, given by this formula, which we have discussed before. This is that formula which we have already discussed just now. It's V1 into square root of C by L. Okay. V1 into square root of C by L. C value is 4 microfarad. L value is 16 and VDC is 200. So if you solve this, the peak current flowing through the capacitor will be 100 amperes. Now, so the peak current flowing to the T1 will be IC plus I mean I out plus ICP. We have also discussed this. So that will be I out will be around 20. I out is 20, right? R is how much? 20 ohms. Oh, sorry. Here R should be 20 ohms. Here there is a mistake. Let me add it over here. This should be 20 because R is around 20. Okay. So if this is 20, what will be the current value? Current value will be 10 amperes. So I out is 10 amperes and IP is 100 amperes. So your main SCR will be carrying around 110 amperes. All right. So just like this, simple numericals can be asked. I repeat, detailed analysis of this class D commutation is not there for you all. Okay. Only thing is explain the working of the commutation circuit and remember the main formulas and solve the simple numericals. Okay. Now they are asking you to find out the diode peak current. Now what is the diode peak current? It is the same as your capacitor current. So what is the capacitor current? 100 amperes. So that will be the peak current of the diode. So this is first numerical. Any doubt in this? This is using the formulas which we have done. Even by analyzing the circuit simply, we can determine this formula, but IP formula you have to remember. Okay, is this clear?
Yes, sir.
Numerical number 1 is clear. Now numerical number 2. Again, we have a class D combination circuit. V1 is given. Now we have a RL load. V1 is 230, L is 20 microhenry, C is 40 microfarad for a constant load current of 120 amperes. Now here we have a load current of 120 amperes. Okay, I out is constant because of RL load actually. Calculate the peak value of current through the capacitor. That means they are asking us to find IP and also through the main and the auxiliary SCR. They are asking us to find ITM and ITA. The circuit diagram is given to you. So also they are asking us to find the turn off time for the main and the auxiliary SCR. So straightforward formula, IP is V1 upon square root of L by C. I mean, here there is some problem. Okay, there should be C by L actually. It should be C by L, square root of C by L. Okay, so please correct it. Here it will be C divided by L, square root of. Okay, so square root of C by L will give you the value of the expression of the current. So IP will be 230 into square root of 40 micro. 40 micro is C value and 20 microhenry is the L value. So you'll get the current as 325.27 amperes once you solve it properly. All right. Now the main current will carry I out plus the capacitor current, which is IP. So I out current is given to you 120. So 120 plus 325 will give you 445 amperes. So that much amount of current is the main SCR carrying. And these are practical situations. The main SCR is carrying around, this much amount of large current. You have SCRs capable of carrying that much amount of current. And what will be the peak current flowing to the auxiliary SCR? The peak current flowing to the auxiliary SCR will be same as I out. So that is I out as it is. You remember we have written these formulas. We are going to use these formulas. Only these four formulas are there. 1, 2, 3, 4. And this omega naught. Omega naught is square root of LC. That's it. So with these four formulas, we have two numericals. Now the turn off time will be of the main SCR will be CV1 upon I out. C value is given, V1 value is 230 and I out value is 120. So it will be simply 78.67 microseconds. Meaning when the main SCR is turning off, it will take 76.67 microseconds to turn it off. It will not immediately go to off state. Similarly, the off time for the auxiliary SCR will be given by pi upon 2 omega naught, where omega naught you can easily calculate. It's coming out to be 35.35 into 10 is to 3 radians per second. So T of time will be pi upon 2 omega naught, and that is coming out to be 44.44 microseconds. So the auxiliary SCR will turn off after 44 microseconds. All right. So using 4 5 formulas of this class D commutator is really important. You have plenty of numericals on that also. All right. So the last PDF of the day. Yeah. Can you identify which commutation is this? Which
C.
commutations are? Yeah, correct. Complementary commutation. You remember T1 turning on, it will turn off. In order to turn off T1, you have to turn on T2. And in order to turn off T2, you have to turn on T1. So this is my complementary commutation. So here we have V1 as 200 volt, R is 100, I mean 10 ohms, R2 is 20 ohms, C value is 10 microfarad. Calculate the turn off time for T1 and T2. So here it is very, very simple. See, this can be asked for 5 marks in exam. T1 is the main SCR, T2 is the auxiliary SCR. So turn off time for T1 is given by this formula, R1 into C natural log of 2, right? So this is the turn off time for the main SCR. You can simply calculate, simply substitute the values over here, R1 as 10, C as 10 microfarad, and this is the natural log of 2. So T off at main SCR will be around 69.31 microseconds. That's the turn off time for main SCR T1. For T2, it is R2 into C ln of 2. So that is coming out to be 138.63 microseconds. So that will be the turn off time for auxiliary SCR T2. So simple two formulas are used over here, but it's important to identify the commutation circuit. And in over here, it is class C. Many times they might not give you the, the name of the circuit. So you have to identify it from the diagram. So this is my class C commutation of for the SCR. You have understood only two formulas are required over here. T off and T off for main SCR and T off for the auxiliary SCR. This is clear to you? So we'll discuss the last numerical of the day. So can you identify this circuit over here? Figure number 3. Which class commutation it is? Hello. Remember class A we have discussed today, RLC series. So this is a class A commutation. So here the value of L, R and C is given, V1 is given. They are asking us the conduction time of SCR and the voltage across the SCR after SCR is turned off. Very simple numerical. Omega naught, it's 1 upon square root of LC. So you can easily calculate omega naught. It's coming out to be 3162 radians per second. And the conduction period of SCR is pi upon omega naught. We have seen that before. And you substitute the value of omega naught, and it's coming out nearby 1 millisecond. Okay. So this is the conduction time for SCR. Now voltage across the SCR, when the SCR turns on, SCR, when the SCR is turned off, the voltage across the SCR is minus V1, and that is equal to minus 200 volt. Okay. So these are all the four numericals which we have discussed related to class D, class C, and class A. So today we have discussed class A commutation, B. So yeah, we have discussed class A, B, C, and D, and we have solved four numericals. Remember, all those four numericals are extremely important. They can be asked in your exams based on the simple formulas. So you have to understand the working of the circuit with the waveforms, and that's it. No need of discussing the detailed analysis, which we have discussed as I've told you today. Only remember the formulas which are there inside the boxes. Okay? Any doubts so far? So we'll end the lecture now, and next time we'll cover class E and EF in brief, and also dual converter topic is remaining. So all that I will cover in coming Saturday or Sunday. I will let you know. And then I'll also cover some part of module number 5, that is AC voltage control and cycloconverter. Okay, everyone. So that will be all for this session.
Okay, sir.
Thank you, sir.